Cool. So we're going to start focusing in on a specific category of compounds. There are lots of different kinds of compounds that have been classified in chemistry. Some that you've looked at already. There was 2 classifications we've made already. The classification is what? We've broken all of the compounds into 2 kinds of compounds. And they had different naming rules. Oh, hi, are you Avery? Come on in. She's in the back. Grab a chair. Okay, 2 kinds of compounds. What are they? We've broken them up already. They gave us different naming rules. Ionic and covalent. Ionic, I-O-N-I-C, and covalent. Ionic was defined to be compounds made up of positive and negative ions. Covalent was made up of 2 negative ions. These guys share. These guys exchange electrons. But there's more. We can break these things up into a whole bunch of more different kinds of these things. So Olivia, she's allowed to be here as long as she's not a distraction to you guys. So you need to have your notes out as well. Yeah, we're doing new stuff. No, the game is done for now. We're doing something new. Okay, so there's a bunch more. And they do show up in these, within these. So the kinds that we're going to look at now, when we're talking about acids, bases, and salts, they show up here as well. Acids, bases, salts. They are all kinds of ionic compounds. They behave differently because of the different ions that are present. Obviously, not all ionic compounds are the same. Acids aren't bases. Neither of these things are salts. But these 3 categories are all ionic. But there's other ones too. One of the things that we've kind of talked about is organic compounds. I've mentioned them to you briefly. Even then, organic compounds, these are typically covalent. Let's go over here. And I've given you, we've talked about it. We haven't done anything with them. I just kind of talked to you about the fact that they existed. But organic compounds are things like hydrocarbons, things like alcohols, and ethers. These are all organic. And there are more. And then there's oxides. There are oxides that are both covalent. So oxides, if we can see this dark green color here, or this kind of teal color here. There's oxides. Or oxides can be either ionic, or they can be covalent, depending on what kind of oxide you have. You can have what's called a metal oxide, or you could have a non-metal oxide. An oxide just means that oxygen is the second element present. Metal oxides would obviously be ionic. Non-metal oxides would have to be covalent. Yes, Brooklyn? That says hydrocarbon. Hydrocarbons. And then as you do chemistry with these things, they create for you different stuff. If you take for example, if you take a non-metal oxide, it will make for you an acid. If you take a metal oxide, it will create for you a base. If you take your your acid and your base, and you combine these things together, those together are going to make you a salt. And so you've now got all these different kinds of classifications of chemicals that have their own classification, and as you start mixing these things together, they do different things. So today we're going to talk about acids, bases, salts specifically, and for the next couple of days. So early chemists. When I say early chemists, I do really mean like at the beginnings of the field of chemistry. So Hands up if you've heard the phrase alchemy. You've never heard of alchemists? So like alchemy was a thing. They were trying to turn lead into gold, among other things. And out of alchemy, something that doesn't actually work, chemistry was born. They started to figure out things. Oh, these are real things that have real properties, and when I react them together, they do different, sometimes useful, sometimes dangerous things. And so chemistry kind of came out of that. Early chemists recognized that there was a few groups. There should be an S here. A few groups of substances each shared common properties. Like within the group, the substances shared a property. One group shared the property that they had a sour taste. Now, you're never going to figure this out in the lab, because over my dead body am I going to let you taste things in the lab? Unless I specifically tell you, yeah, go ahead and eat this, I will not let you eat things in the lab. But at the beginning of chemistry, we didn't know this, so people were tasting things because it's one of your 5 senses. It's a way to put these things together. And what they discovered was that there was a group of compounds, they all shared this sour taste. They named this group of compounds acids. Not always, because the last I checked, a lemon, an orange, a lime didn't kill you. But all 3 of those contain a particular kind of acid. What is the acid found in lemons, limes, and oranges? Well, they are citrus fruits, and so the acid found is called citric acid. It's also found in a crystal form. It's what you put on top of gummy worms, sour keys to make them sour. That is citric acid in a crystal form. I love it. It tastes great. But there's other acids that are less desirable, some that you still can't taste. Yesterday, after school, I went and I picked up my daughter from daycare. She was complaining of an upset stomach, and she was crying, and so I was comforting her. And then I put her in the car, and we were driving home. It's about an 8-minute drive from my home, from my daughter's daycare to our home. And in that time, she said, my stomach really hurts. I turned the mirror so I could see her face. Her eyes went wide, and then she projectile vomited all over the inside of my car. Thank goodness for headrests, because I would have worn it on the back of my head had that not been there. But, and the reason I say that is because something that accompanies that act is an acid your body produces, which is why when my daughter threw up, there was a very sour smell permeated my Corolla, which is awful. But you have that taste. You kind of have a sour taste in your mouth when it's done. That's because your stomach produces an acid. Obviously, it doesn't kill you because if your body's making it, you can throw it up. What's the acid produced in your stomach? Does anyone know? We've actually talked about it a few times without giving it that label. Your stomach produces an acid called hydrochloric acid. Your stomach also has a lining of mucus on the inside, because if you don't have that lining of mucus around the inside of your stomach to protect you from the hydrochloric acid that's there, what do you develop? There's a medical condition that you will develop if you don't have that mucus protecting the inside of your... No, it is not Whipple's. It starts with a U. An ulcer. An ulcer shows up when the mucus lining of your stomach isn't there to protect it from the hydrochloric acid that's constantly trying to break down whatever's there. And so that goes away, for example, I've had family members who decided to abuse certain other substances on this list. And if you abuse this one of the effects is a decrease in that mucus. And so my cousin developed pretty intense stomach ulcers. And if you let that go long enough, they can actually perforate, which perforated stomach ulcer means now you have a hole from the inside of your stomach to the outside of your stomach, and now that hydrochloric acid is allowed to run rampant over your entire inner cavity, which is really, really bad. That can kill you. So you have this particular, there are acids that your body produces for a particular task that on their own are dangerous. Could you taste it? Yeah. But if you chronically throw up, and there are conditions where this is a thing, it damages your teeth, it damages your esophagus, because inherently these acids are dangerous, but they have common properties. Evelyn. No, it just has a lot of calories, makes you fat. Alcohol just has a ton of calories. Okay, so acids. One of the properties they share is sour taste. They've got other properties that we'll outline, but one of them is that. Another group, so they have the acids. They're like, okay, cool. They all have a similar sour taste. Some of them killed Joey, but the rest of us, we tried these other acids and they were okay. But there's another group that they tasted and they're like, okay, these things, which they called, I'll come back to this in a second, they all felt slippery. They felt these things and like, oh, this is kind of slippery. They were also good cleaners. This thing was dirty. We put this slippery thing on the dirty thing, and now the dirty thing is clean. That's weird. And in addition to that, tasted bitter. These three things together, and it's interesting because there are some bitter things that we consume that are also acidic, like coffee. Coffee has a bitter taste, but coffee itself is acidic, and so there is some kind of there's a little bit of overlap there. But the things that were slippery were good cleaners and tasted bitter. They called alkalis, which is where, if you remember back to grade 9, looking at the periodic table, you had the alkali metals and the alkali earth metals. And I mentioned up here that when metals react with oxygen and then you dissolve them in water, or when they react with water directly, they form a base. One of the things I did with you the last year, or my student teacher would have done with my students last year, was he took sodium, an alkali metal, tossed it in water, thing goes boom, but then when I do it, I don't know if Mr. Gebrand did it last year, but when I do it, I tell my students, come up, feel what's just happened here. And the water is no longer just water. Now it's got this slippery texture to it. What you've made is an alkali. You've made a base. Specifically, you've made sodium hydroxide, which is an ingredient in bleach. That's why bleach is a cleaner, because there are compounds there that have properties of, well, they're slippery. They were good cleaners. We call them bases. So the word here should be in. In the 1800s, a Swedish chemist named Svante Arrhenius, which is a great name. My wife didn't go for it when we were naming our son, but Svante is a great name. Svante Arrhenius was studying these acids and these bases, and he recognized that if you look at all the formulas for all the acids, and you look at all of the formulas, chemical formulas for all the bases have one thing in common, all the acids have one thing in common, and he realized that when you dissolve acids in water and bases in water, it was actually the presence of a particular ion in each case that was really what made something acidic or made it basic. And so his definition for acids and bases changed what had come previous. In 1903, so as far as science goes, this is recent. This is within the last 130 years. This is recent chemistry. He defined acids and bases this way. He said that acids, whatever they are, when you dissolve them in water, produce H plus ions when dissolved in water. So, for example, if you took HCl crystals and you dissolved that crystal in water, if you put this and you dissolve it, what it's going to do is actually the water will separate out the H plus and the Cl minus ions. They'll float around freely until you boil the water away, and then the hydrogen ions and chlorine ions will come back together and they'll recrystallize, creating you HCl. It's this guy right here that makes it acidic. Bases produce OH minus ions when dissolved in water. Sahib, your grade 12? Oh, shoot. Okay, never mind. There is another definition for what makes an acid and what makes a base. I'm not going to tell you what it is. There is, in fact, a newer definition for what makes an acid and a base, and if I'm not mistaken, you'll see in grade 12. Put together by two, I don't remember if they were men or women, but two chemists by the names of Bronsted and Lowry. They have a new definition for it. You'll see it in grade 12. For obvious safety reasons, scientists do not rely on taste tests to classify compounds in the laboratory. Instead, other properties are used, which we're going to look at today. Okay, when you're ready, flip the page. So, let's talk about acids. Acids are fun. Acids are chemical compounds that release hydrogen ions. We've said it before, we'll say it again. Hydrogen ions. So, H+. In an aqueous solution. That word aqueous means dissolved in water. When you're talking about acids in general, what chemists will do is that the general formula for an acid is, they say it's HA. The H gets listed out front because that's the thing that defines the acid as the acid. And then this letter A here just represents the rest of the formula, whatever it is. So I've got a list actually on the bottom of this page of common acids. I'll come back up to this section in a second. But just to show you what I mean here, this HA, every single one of these acid formulas that are down here, HCl, H2SO4, HNO3, except for this guy, but H3PO4, H2CO3, and HF, all have the H listed out front. Sometimes this guy right here is actually listed as HCH3COO. And when I say, so up at the top of that generalized formula is HA. For HCl, obviously the A would be replaced by Cl. For H2SO4, the A would be replaced with SO4. NO3 would replace the A. The CH3COO would take the place of the A. Up here in that generalized formula, it's just whatever is the rest. So there are binary acids. Binary means what? What does the word binary mean? Means two. So a binary acid, binary means two, is made up of two elements, hydrogen and a nonmetal, a nonmetal, such as chlorine. We'll talk about HCl a lot because you guys are intimately familiar with HCl. For example, your body makes this thing and everyone pukes, so everyone digests. Hopefully you all had something to eat about an hour ago. Your body is using the HCl that you've got right now to do a job. But then there's other things called oxyacids. The oxyacids are made up of hydrogen, oxygen, and generally speaking, one other element. For example, H2SO4. The oxyacid here is hydrogen and oxygen. The other element is sulfur. And down here, the other element is nitrogen. Down here, the other element is carbon, phosphorus. This one's got another carbon. This one's got fluorine. All nonmetals. So you got binary acids, you got oxyacids. The formula of acids usually starts with the presence of one or more hydrogen atoms. There are exceptions, but as a general rule, the hydrogen is always listed first. For example, something like H3PO4. And I've already said it. We'll formalize it right here. This particular acid you will need to be told that this thing is an acid. Actually, hold on. Never mind, I take it back. That is the formula for the acid. Also seen like this. Again, I'm being repetitive, I know, but that's okay. And then this thing right here is a polyatomic ion. What's that polyatomic ion called? So, that's acetate. Isn't acetate in some forms it is. Depends on what it's with. In this particular form, it's not dangerous. Yeah, that is a COO. Because this thing, I'll skip this blank for a second and go down here. Acetate here, HCH3COO, called acetic acid, also called ethanoic acid, is not dangerous. In fact, some people quite like this acid. Generally speaking, they put it on potatoes. No salt, salt. What is the acid that sometimes gets dressed upon potatoes? Oil's oil. Balsamic what? Vinegar. Acetic acid is vinegar. So you have salt and vinegar chips. Vinegar is an acetic. That's why it gives you kind of that sour zip. It's because you're consuming an acid. It's yummy. Some people think, yeah. What do you mean? In some forms, acetate is. You can bind acetate to other things. I mean, you can get a simple example. I mean, oxygen on its own is not dangerous. You're breathing it, your body needs it. But you combine oxygen with basically anything else on the table, you can make varying degrees of dangerous compounds. And again, even danger depends on what you do with it. Oxygen's great. If you take hydrogen and oxygen, bind them together, you can make water. Water, we don't think of water as being overly dangerous, but if you do the same thing with water that you do with pure oxygen, what's going to happen? What do you do with oxygen? Where does it go in your body? What if your lungs. What if you took the hydrogen that you just put together with the oxygen and put that in the same spot? That is called what? Drowning. So, I mean, when you talk about dangerous, everything is if you misuse it, and nothing is if you don't misuse it. I mean, if you're on a bad date and you find yourself in a dangerous position, and you then had your salt and vinegar on your fries, yummy, quite tasty. Someone makes a pass the wrong way and you throw vinegar in their face, that's going to be wildly painful. Vinegar will be an acid, it'll burn their eyes. It would be a horrendous experience. But if you put the vinegar in a different hole, it tastes yummy. So again, the idea of danger, very relative, if that makes any sense. So common acids, most are ionic compounds. Not all, but the vast majority of them are. Hydrogen and nonmetals, or hydrogen polyatomic. So here's some common ones. Here's what they do. HCl has 3 different names. Sometimes it's called muriatic acid. Sometimes it's called hydrochloric acid. Sometimes it's called gastric acid. Because of all of its different purposes, it is used in producing plastic. It's used in processing metals. Like when you mine ore out of the ground. Have a great day. I'll see you tomorrow. Okay. Ooh, win. Good luck. Hydrochloric acid is used to process the ore out of, like gold out of gold ore, for example. Or gastric acid, because it's also used for dissolving food. Dissolving food in your stomach. Sulfuric acid. Sulfuric acid is always dangerous. Sulfuric acid is fun to play with. Don't do it. I'll do it for you later. Sulfuric acid is used in car batteries, among other things. But that's its most common regular purpose. Nitric acid is used in the makings of explosives and fertilizers for crops. We've already written it down, but ethanoic, also called acetic acid, is vinegar. Makes food taste yummy. Phosphoric acid is used for a bunch of things. It's used in flavoring for foods and beverages, used in dental products, used in cosmetics and skincare products. Yeah. No idea. Your guess is as good as mine. Carbonic acid is another one that you regularly consume. Some of you regularly consume. Carbonic acid is found in, carbonic acid gets made in, it shows up in, it's not there to start, but it gets produced in carbonated drinks. Because if you look at it, it's H2CO3, which if we break that formula up a little bit, this is H2O and CO2. But if you take the H2O and CO2 and you pressurize it, you force the CO2 into the solution, you make carbonic acid. That's why you toss a nail in Coke, it dissolves. Well, it's one of the reasons. There's other things in Coke that will dissolve a nail, but carbonic acid's present. That's why you drink a lot of pop, it rots your teeth. Yeah. Yes. They'll take, well, there's other things in it too. They'll take pure Coca-Cola syrup and use it to clean highways after car accidents because it'll just eat through everything. Coke's really bad for you for so many reasons. The sugar, some of the other compounds that are in there. Oh yeah, Coke's terrible for you. Tastes good though. The carbonic acid, any carbonated drinks, carbonic acid is present. But if you look at what's happening, what happens here, when you crack the seal on a carbonated beverage and let it sit, all the bubbles go away. The bubbles are CO2, and then the beverage tastes flat. Why does it taste flat? Because you've added a bunch of water to it. The CO2 leaves out the top, and the extra H2O that was a part of the carbonic acid makes your beverage taste watery. We call it flat. The pop is now flat. That's just because a bunch of water got added to it. Or you've got hydrofluoric acid. This is made in manufacturing and etching glass. There's a few more we'll list here at the bottom. One of them is HC6H7O7. This is citric acid, found in fruit. Any fruit that's labeled as citrus, that's the acid that's there. You've got this one, C3H6O3. This is called lactic acid. It's used as a food additive, also builds up in your muscles when you exercise. So there's a whole bunch of different, those are acids. I know I've only got 10 minutes left, but we're going to keep going. Bases, when you're ready, flip the page. So, acids, hydrogen ions. Bases are compounds that release hydroxide ions. Don't worry, I'll tell you when to pack up. Some of you are just itching for it. OH minus. In an aqueous solution. So again, dissolved in water. You take NaOH, you dissolve it in water, you'll get the Na ions, and you'll get the OH minus ions. You dissolve out the water, this thing will recrystallize. Daniel and Massey, put the soccer game away. Not soccer today, we're just messing around? Okay. Gentlemen, stop it and pay attention. The general formula, if an acid was HA, the base is probably going to be what? No, it's not HB. No, H was an acid because acids produced hydrogen ions. This produces OH ions. The general formula for an acid was HA. Because it was an acid, acids produce hydrogen ions. The generalized formula for a base, if a base produces an OH minus ion, is going to be No, BO. BOH. Base is made up of a positive ion and hydroxide. An acid was made up of hydrogen and a negative ion. So base, the letter B, and OH. We encounter bases every day. The bitterness, coffee is a complicated one because coffee does have an acidic property, but it also has a basic property, and the basic property of coffee is what dominates the flavor. So the bitterness of coffee, the slipperiness of soap, or the slippery feel of soap, are due to basic compounds that are present there. Most of them, again, are ionic, made up of positive metal and the negative hydroxide ions. These are some examples. So NaOH is also known as sodium hydroxide, or that it is sodium hydroxide. It's also known as caustic soda or lye, used as a drain cleaner, oven cleaner, used in making soap and paper and in water treatment. And if you've seen the movie Fight Club, it's what they use to dissolve bodies, because lye will do that. Dissolve a body. Not sure if you need that piece of information. Might be useful at some point in your life. I hope it's never useful. Not into thin air. Into itself. Everything. Chemistry. Well, that's what dissolving is. You add something to water and it breaks it down. The things are still there. You take table salt crystals, you put them in water, they dissolve. They're still in the water. They're just broken up. You can't see them anymore. Yeah, into the individual ions. Caustic soda will do the same thing to a human body. It's pretty intense. I mean, if you think about it, even like a drain cleaner or an oven cleaner, those things are nasty compounds. MgOH2, magnesium hydroxide, used as an antacid or a laxative. I'm going to demonstrate this one for you. It's an over-the-counter. If you have, so an antacid, if you have heartburn, that's because your stomach acid's coming up out of your stomach into your esophagus. Your esophagus doesn't have that same mucus lining that your stomach does. It burns, but it's not your heart that's burning. It's that tube that connects your mouth to your stomach. That's what heartburn is. To get rid of that, we take Tums, or we take milk of magnesia. Tums are chewable tablets. Milk of magnesia is a liquid. I will demonstrate this for you in the lab. Not today, but I will. Another one is calcium hydroxide, uses soil and water treatment. NH4OH, also called household ammonia, which is confusing because this is ammonium, but they call it household. You go to the store, Save on Foods, you buy a jug of ammonia. It's not NH3, it's NH4OH. It's used as a cleaner, a refrigerant, a food additive. In some cases, wildly dangerous, because ammonia will kill you. But it's a food additive, so, sometimes it's yummy. Potassium hydroxide, KOH. Has similar uses to NaOH. It's also used in batteries. So the bases are, the acids are like, for lack of a better word, like the sexy, scary compounds. People are like, ooh, acids. Ooh, acids. People are like, oh, bases, whatever. Soap, fun. No, these are, the bases are so much worse than the acids ever will be. The acids are just flashier. They do what they do, just more exotically. And I have created a table. Well, I didn't create it. I ripped it off your textbook. That you will need tomorrow when I assign you a bunch of questions where you compare acids and bases to each other. And this is where I'm going to end today. I'm not going to go through this table. You're going to need to read it tomorrow. And I'm done. 5 minutes left. Acids and bases. Welcome to the wild and wacky world of chemistry. Again, it's cool stuff.